Hi, everybody. I hope you're doing well. Today, we're going to introduce our last big subject, nuclear physics. So far, we've talked about quantum mechanics, and we use quantum mechanics to describe atoms, principally the hydrogen atom. And now, today, we'll be able to turn and talk about the center of atoms, the atomic nuclei. In this lecture, we introduce the basic properties of nuclei. What are they? What kind of nomenclature do we use to describe them? And then some of their properties. What's the size of nuclei? What's their density? And what's their binding energy? After that, in future lectures, we'll talk about more of the physics. Okay, hang on for a second. Okay. There we are. So we've talked about atoms up till now. And atoms, which contain light electrons, can be thought of as objects with a characteristic size of the order of 1 angstrom. The atomic nucleus, on the other hand, is about 10,000 times smaller. It's a tiny ball. And what's more, it contains almost all of the mass of the atom. Atoms are made up of protons, neutrons, and electrons. Compared to electrons, protons and neutrons have masses about 2,000 times larger and nearly equal, although the mass of a neutron is slightly higher than the mass of a proton. We'll call neutrons and protons nucleons. They're the components of the atomic nucleus. One more thing, just like electrons, neutrons and protons are spin 1/2 particles, which means that they're fermions, which obey the Pauli exclusion principle. Here's some nomenclature. When we describe an atomic nucleus, we can talk about the number of protons it contains and the number of neutrons it contains, or the total number of nucleons it contains. The number of protons is a very important number because it determines what kind of atom we're talking about. And Z, the number of protons, is called the atomic number. On the other hand, A, the total number of nucleons, determines the mass of the atom. And so A is called the mass number. The notation that's usually used is this. There's a symbol, a chemical symbol for the element. And then in the upper left-hand corner, we give the mass number. And in the lower left-hand corner, we give the atomic number. So for example, here's the symbol for iron 56. Iron contains 26 protons. So Z is in the lower left-hand corner. And the most common isotope contains 56 nucleons in total. If you want to know the number of neutrons, of course, you can just figure it out from A and Z. Okay? By the way, sometimes the atomic number is omitted since it's really also determined by the chemical symbol. Okay. Another piece of nomenclature, nuclei or atoms come in different isotopes. Isotopes are nuclei that have the same Z, the same number of protons, thus they're the same element, but they have different numbers of neutrons. So the atoms have different masses. Okay? This is a schematic chart of nucleotides showing a graph of the neutron number versus the, I believe, the Z number, the atomic number. Okay? It's interesting to look at this. In this chart, the dark blue points are stable nuclei. The light blue points are unstable nuclei. And then outside of those ranges, there's nothing, no nuclei have been observed. For light nuclei, you can see that the number of neutrons is close to the number of protons. The stable elements are close to this dashed line where N equals Z. But it's interesting to see that for heavier nuclei, the chart deviates from this line. Heavy nuclei are always neutron rich. In any event, for a particular atomic number, we can have multiple different isotopes. And just for example, this shaded region shows the different isotopes of carbon, such as carbon 11, carbon 12, carbon 13, carbon 14. Okay, they all have 6 protons, but they have either 5 or 6 or 7 or 8 neutrons. Okay, of these, carbon 12 is the most stable, the most common isotope of carbon, and most of the others are unstable. They're radioactive and decay to other nuclei. Okay, as we've mentioned, nuclei are very, very small, and they're very, very dense because they contain nearly all of the mass in the atom. What we'll see is that a nucleus can be thought of, if you like, as a tightly packed ball of nucleons. And as a result, the volume of a nucleus is approximately proportional to the mass number. Okay? Basically, it's A times the volume of each nuclei, more or less. Since this is a ball, or a sphere, we can think of this as a sphere. The radius of that sphere should just be proportional to A to the 1/3. Okay? And so we can write it in this way. R sub A is equal to R0 times A to the 1/3. And empirically, it's found that R0, this constant, is about 1.2 times 10 to the minus 15 meters, or 1.2 femtometers. And this would seem to be something like the size of a proton or a neutron. Just to use an example, carbon 12, the radius of this atom, of this nucleus, should be R0 times 12 to the 1/3, which gives a size of 2.7 femtometers. Now, if we're clever, we can use this to figure out the density of an atomic nucleus, because this formula gives me the volume, and then we can just look up the mass. For example, okay, to find the density, which is the mass over the volume, we can simply take the mass to be A times the atomic mass, the atomic mass number times the mass per nucleon U, and then divide that by the volume, which is 4/3 pi r A cubed. And then substituting here, R sub A cubed would be R0 cubed times A. And making that substitution, we'd find that the A's cancel out, and we're left with a density for atomic nuclei, which doesn't depend on A, okay? And it works out to be 3U over 4 pi R0 cubed. Now, we have values for all of these things, so we can go ahead, if we like, and figure out the density of atomic nuclei, approximately, using this formula. So why don't you go ahead and do that, and I'll ask a reading question in just a moment. Okay, if you've worked that out, you should have found that the density of an atomic nucleus is about 2 times 10 to the 17 kilograms per meter cubed. This is about, I believe, 200 trillion times the density of water. Another way to think of it is it's about 1,000 aircraft carriers per cubic centimeter. It's a fantastically high density, okay? And it comes about because of all the mass of an atom is concentrated in this tiny, tiny object. Okay, sorry, 1 second.